Here we will discuss the concept of the inner product, which is a generalization of the dot product that we've seen in multivariable calculus and linear algebra. We'll also discuss orthogonality and the norm of a vector. First, let's recall the idea of the dot product of two vectors. This was the way of taking two vectors and getting a scalar that represented something about the relationship of those two vectors to each other. You can think of the dot product as a function that has as its input two vectors and the output is a scalar. This idea can be generalized to obtain many different functions on any particular vector space, and we call these inner products. This is a function that takes two vectors from V and returns a scalar. However, these inner product functions must have a few more properties in order to be analogous with the dot product. First, the inner product must be symmetric, so u times v must be the same as v times u. Second, it has to be linear in the same way that the product of two numbers is linear. So scalars can be pulled out of the product, and a distributive property exists over summation. Finally, the inner product of a vector with itself must be non-negative, and only zero when the vector itself is zero. As an example, let's consider a modified dot product on R2. Consider these two vectors u and v. We define an inner product on R2 by the following rule. This has some similarities to the dot product, but is obviously different. If you are unsure if this inner product function satisfies the three properties, then feel free, take a minute to check them for yourself. It's not terribly difficult. Using this inner product, we see that the inner product of u with v is equal to 10. This example shows that many inner products can exist on the same vector space. Usually when we choose a vector space, we also set the inner product with which we are going to work. There's often a typical inner product on vector spaces, though. In this class, we will work mostly with function spaces. And those are vector spaces that involve functions such as CAB or CKAB. The L2 inner product is the common one that is used for vector spaces. It is defined by multiplying two functions f and g together and then integrating across the domain, the interval AB. So we see again that the inner product is taking two vectors, functions in this case, and outputting a scalar via integration. For example, let's take the two functions f is equal to sine of pi x and g is equal to cosine pi x. By multiplying and integrating these two functions, we see that the L2 inner product is in fact equal to 0. This is actually quite interesting and relates to an idea that we learned about in linear algebra, which is orthogonality. Recall that if the dot product of two vectors in R2 or R3 is 0, then those vectors are going to be perpendicular to each other. Here we have an example of two vectors in R2. They are obviously perpendicular to each other, and when we compute their dot product, we get 0. While the geometric meaning of perpendicular does not necessarily extend to other vector spaces, such as function spaces, many of the properties of perpendicular vectors does extend. Therefore, we use a slightly different terminology. For any general vector space, we say that two vectors are orthogonal if their inner product is 0. So while we can't really think of two functions being perpendicular in a geometric sense, we now have some way of defining a similar idea no matter what kind of vector we're talking about. All of the algebraic properties of perpendicular vectors translates very well to orthogonal vectors. The one of interest to us right now is that if two vectors are orthogonal, then they are going to be linearly independent. Next, we define the norm of a vector. This is very analogous to the absolute value of a scalar, and actually exactly the same as the norm you learned about in multivariable calculus and linear algebra. The norm is a function from a vector space to R with the following properties. First, the norm of a vector must be non-negative. Second, scalars can be taken out of the norm, but when they're taken out of the norm, they have to be put in absolute value. And finally, we have the triangle inequality, which is the same inequality that you know from the absolute value. When an inner product is defined on a vector space, we can use that inner product to compute the norm. The norm of a vector is equal to the square root of the inner product of u with itself. So we can now see why the inner product of a vector with itself has to be non-negative, otherwise we'd be taking the square root of a negative number. The basic idea of a norm is that it defines the length of a vector. In R2 and R3, this makes intuitive sense, since we could stick a ruler on the vector and actually measure its length. However, this can be extended to consider the length of other types of vectors, such as functions. For instance, we can determine how long the function cosine of pi x is in the space of C01. Using the inner product, we take the square root of the integral of f with itself, and we see that the function has length 1/2. However, we often don't really want to know the length of a function, uh, such as the solution to a differential equation. What is of interest, though, is the distance between two functions. This can be calculated by considering the norm of f minus g. You can see how this might be interesting when we are approximating solutions with algorithms. You want to know how close your approximation is to the exact solution. The norm will tell you the distance between your approximation and the exact solution. Obviously, you want the norm of the difference of those two to be relatively small. When we use the L2 norm to calculate the distance between functions, we often use the term mean square. So for instance, we might say that two functions are close or far away in the mean square sense. For an example, let's take these two functions f and g. Notationally, they don't look very similar at all, but by considering the norm of f minus g, we see that they are in fact relatively close in the mean square sense. They have a distance of 0.00694. Now, this does not mean that the functions are necessarily close at each point in the domain. Here we can see a graph of the two functions, and we see that they're, in fact, very often much farther away from each other than the distance of 0.00694. This mean square sense, the L2 norm, simply tells us the distance of the two functions on average over the interval.